Okay, so welcome to the second half of this tutorial where the mystery will be revealed.
Yeah, so I ended the first lecture at the point where I said that somehow community organization seems to be promoting or enhancing the persistence of diseases. Okay? So diseases which would have otherwise ended very quickly, for example, in a homogeneous contact network where everybody, kind of has, in some sense, equal likelihood of contacting anybody else, it would have quickly died out. But if you have a network which has tight community organization, it stays around for extremely long times. So why? Okay, so one way to try to understand this is to use the theory of diffusion processes on networks, and in particular on modular networks. So the simplest example of a diffusion process on a network is to study how random walks progress on graphs. So for example, if you take a random walker on a model of a modular network, and you try to understand how it differs from the walk on a Erdős-Renyi random graph, you immediately find that whereas the distribution of first passage times, so first passage time is essentially, let's say you declare that after how long does the walker reach a particular designated position. Okay? So if you look at the distribution of first passage times, on Erdős-Renyi graphs, this is how it looks like. Now, if you look at the same distribution, but in a model graph with community organization, then you find that for intramodular and intermodular processes, actually the distribution is very different. And let me just not detail at this point because I'll talk about this in length in a few more slides. So essentially, let me give you a hint of the reason before expanding on it. So the reason that we see this extremely long persistent time scale for epidemics has to do with the fact that there are actually two distinct time scales exhibited by modular networks. A fast time scales at which we have intramodular diffusion, and a very slow time scales at which we have intermodular diffusion. Okay. And this kinds of distinct time scale behavior is not shown by homogeneous networks, in particular random networks. And so what is the answer in one word, on one sentence, is that in modular networks, the disease spreads very slowly from module to module, thereby allowing parts which it has already left behind to go back to susceptible state. So when the disease comes back after completing one circuit, so to say, it finds a batch of fresh susceptible individuals to infect again, and that's how the epidemic continues on and on. Okay. So how do you actually validate all of this? So empirical networks are fine, but then the problem is that you can't tune the modularity in a controlled fashion. So one of the simplest model networks which you can take, where you can tune the modularity and try to understand the role of modularity in making the disease persist, is one where essentially you take a group of random networks, and then you connect these random networks to each other with a designated connection density. So if you look at the adjacency matrix, if you have completely isolated modules, this is how it looks like. So here you have 5 isolated modules. The black dots essentially represent connections between any pair of individuals in the row and the column. So this is a matrix, right? So essentially, if you look at this row and let's say this column, then if the corresponding entry is 1, it is colored black in this graphical representation of the matrix. So what you vary in order to study different kinds of modularity is the ratio of the intermodular connection density to intramodular connection density. Or in other words, let's say you take the graph, and this is its adjacency matrix. Okay, so you say that these are, let's say, the within module connection density, and the between module connection density is designated rho I, and so the ratio of rho I to rho O is the quantity, is the parameter which characterizes how modular a particular network is. So not surprisingly, the range that it varies is between 0 to 1. Well, if you take equal to, essentially you get this limit. So R equal to 0 corresponds to completely isolated communities. So no connections exist between the different communities. And R equal to 1 essentially corresponds to a homogeneous random network. So in both of these extreme limits, it's pretty easy to understand what will happen. So in the case of isolated communities, you'll have epidemic breaking out within a particular community, and it will infect probably the most of the people in that community and then just die out because it can't break out of that community. Whereas for the homogeneous random network, essentially the behavior is going to be very similar to that predicted by this homogeneous mixing models. Yeah. Rho is the connection density, yes. No, we're not talking about if the densities are same in the different modules, that's okay, because what we're looking at is the ratio of the between module density to within module density. Okay, of course you could vary this also. That's another possibility. But in the simplest case, you just take these densities to be the same, but these densities are different from these densities. So for example, you could take this density to be 1 and this density to be, let's say, 0. Okay, that's one extreme case which would correspond to this. Sorry? How are they computed? No, so this is essentially a model network where, for example, you are constructing an ensemble of such graphs. So you say that you write a program which would generate this kind of adjacency matrix. So you tell it what average degree and what R you want, and then you can find out what is the corresponding rho naught and rho I. So one way is, so I think the maths would be very similar to what Chris was talking about in yesterday's lecture. So essentially one way to do this is just to ask, okay, how many modules do I have? So suppose this is an n by n matrix, and suppose you have m modules. Okay, so then the size of each module, in the simplest case, let me just take equal size modules because that will make the maths very easy. So let's say small n, the size of each module is n by m. Okay, so then this is n. Okay, so then n rho naught plus n minus n rho I is k, the average degree. Okay. So, and you have this other relation which says that R equal to rho I by rho O. So what you do is you replace this by R rho O and you solve for rho O. Okay. So if you give me M, if you give me capital N, and if you give me K, I can tell you what is rho I and rho naught required for constructing that particular modular network. Okay, so here I'm showing 3 different agency matrices corresponding to R equal to 0, R equal to 1, and some intermediate R, let's say 0.1. Okay? And so you can study the persistence of the epidemic in these kinds of model networks, and you see behavior very similar to what you see in the case of the empirical networks. Essentially, there is some optimal modularity at which the probability of persistence of highly infectious diseases is maximum, and it kind of goes down either for completely isolated modules or for homogeneous networks. Now, yeah. Okay, so this particular spreading is the SIRS model. But you can understand the mathematics behind it just by simple random walk process. Okay, let me just cover this and then maybe we can. Yeah, so this is just the SIRS model. Okay, so so I mentioned before that the random modular networks are essentially small world. So in the case of this particular model, modular networks, you can actually study properties like the average path length, or rather what we study is the reciprocal of that, which is termed communication efficiency. And you can look at the clustering coefficient. And if you look at how these quantities differ with R, the ratio of intermodular to intermodular connection density, you find that it behaves almost identically to the way that average path length and clustering coefficient varies with P, the fraction of long-range shortcuts in Watts-Strogatz networks. In fact, even if you measure the Newman measure of modularity Q, it turns out it's very hard to actually differentiate between these kinds of modular networks and Watts-Strogatz network using just only this parameter. However, where they do differ is the existence of these two timescales in the modular networks, which is not shown by Watts-Strogatz network. Okay? So when we look at how the persistence time of an epidemic behaves as a result of increasing the infectiousness of the disease, which is characterized by this basic production number. So let me remind you, basic production number essentially means the average number of secondary infections caused by a single primary infection. So if it is greater than 1, that means you have an epidemic. That's the definition of an epidemic. And the higher it is, it means the more quickly it's spreading. And in the other axis, what we have is the ratio of the intermodular to intramodular connection density. So at this limit, r equal to 1, you get essentially a homogeneous random network, whereas at this limit, you have modules which are almost isolated. So what you notice is that if you take any one particular value of the basic production number, so essentially you fix the contagiousness of the disease. So for example, here we have fixed it to 8.5, and you look at the persistence probability, you find that the persistence probability peaks at some optimal range of R, which means that there is an optimal range of modularity at which you have maximum persistence of the disease. And qualitatively, it's easy to see why this is happening. So if you have a very low value of R, where the modules are almost isolated, what's happening is that the disease has a local breakout in a particular module. You could have multiple breakouts in different modules, but the disease can't spread beyond the local module or just, let's say, its immediate neighbor. After that, it just dies out, okay, because it cannot jump to another module. There are just too few links. On the other hand, if you've got essentially a homogeneous network, so at r equal to 0.02, that's almost effectively like a homogeneous network because you've got lots of connections between connecting the different modules. The disease essentially spreads like wildfire. Okay? So within a very short time, essentially everybody else in the network has got the disease, and then they recover almost simultaneously. And so therefore, the pathogen cannot find any further susceptible individuals, and it dies out. So in both of these cases, you find that the disease, very quickly after the local outbreak dies out. But in the case of an optimal range of modularity, the epidemic has a local outbreak in a few modules. Then after a while, it manages to jump to another module. And after a while, it manages to jump to another module and so on. But each of these intermodule jumps is taking so long that by the time it completes its circuit around the network, there are parts of the network which have now recovered and which it can now infect all over again. So you find that you have this white and black. So the orange corresponds to susceptible, the white corresponds to infecteds, and the black correspond to recovered. And you find that you have wave after wave of fresh infections which go on through the system, which is manifested by this kind of periodic, almost periodic oscillations you see in the incidence of the disease with time. If you look at it in terms of the distribution of the times, or the distribution of the persistence times, you find that as a function of R, so if you have extremely low value of R, the persistence time is actually extremely low. And if you have high value of R, again, the persistence time is kind of distributed around a very low value. But at some intermediate value of R, you have two possibilities. You have a few cases in which there are local outbreaks which quickly die out, but in several other cases, you have many realizations in which the disease stays around for an extremely long time. And as you increase the number of modules, this effect becomes even more prominent. So how do we understand this? So essentially, you go back to this random walk approximation that I was mentioning. So if you consider a set of random walkers moving on networks such that, so rho I is, let's say, the fraction of random walkers which are at node I in time t, and so therefore the sum over I essentially gives you 1. So you can write down a local continuity equation which tells you that what is the change in the density of walkers on any node after an unit time. So if you look at the difference of rho I at time t plus 1 with rho I at time t, you can think of this as an inflow minus an outflow. So inflow tells you the process by which walkers from other nodes are flowing into the ith node, the node that you're in currently, a node that you're interested in currently, and the outflow is telling you how the walkers in the ith node are essentially moving out to other nodes. So you can write it down as a master equation, where rho is, again, this density of walkers, so to say. So essentially, the master equation relates the difference in the densities at time t and time t plus 1 to rho and the diffusion matrix, which is essentially the adjacency matrix divided by the degrees of the nodes minus identity matrix. And this is what makes life interesting, because if you are familiar with Laplacian, it should take you a very short time to realize that this diffusion matrix is in fact nothing other than the negative of the Laplacian by the degree. Okay? So the Laplacian matrix is something that which occurs again and again in the network context. Essentially, it's the degree matrix, which is a matrix which tells you, on its diagonals, what are the different degrees. Okay, so it's a diagonal matrix with just entries along the diagonal, k1, k2, kn, where ki is the degree of the ith node. And you subtract from it the adjacency matrix. So, here you have, let's say scores of zeros and ones, and so on. And the difference is essentially this Laplacian matrix. So the diffusion matrix is essentially very intimately related to the Laplacian matrix. And you can think of the evolution of the Walker distribution as given by this kind of a discrete time equation, where the density at time t plus 1 is equal to the t times the density at time t, and T is this transition matrix for the Markov chain defined on the network. So if you start from, there's a typo here, it should be rho 0. So if you start from some initial density, rho 0, then T is actually acting like a time propagator. And although T is not symmetric in general, you could relate I minus T to the symmetric normalized Laplacian by similarity transformation, which in other words means that they have the same eigenvalues. So in other words, to look at the time scales taken by such walks, you can just look at the eigenvalues of the Laplacian, and a difference in time scales of this diffusion processes would appear as a gap in the spectrum of this matrix, and therefore by extension the gap in the spectrum of the Laplacian. So using this knowledge, you can now look at the Laplacian spectrum for different values of R. So what you notice is that as you decrease R, suddenly a gap opens up in the eigenvalue spectrum. And the gap keeps widening as R decreases further and further, which in other words tells you, so one way to think about this is simply this: these modes essentially correspond to intermodular diffusion timescales. Okay? The time it takes to jump from one module to another is essentially governed by these modes. Whereas the bulk essentially controls the intramodular diffusion timescales. In other words, the time taken by processes to move within each module. Okay? So you find that the time difference between intermodular processes and intramodular processes becomes wider and wider as R becomes smaller and smaller. Okay? In contrast, if you look at Watts-Strogatz network and look at its Laplacian spectrum, you find that no such gap occurs no matter how much you change P. So although you do have structural similarities between Watts-Strogatz small world networks and modular networks, in other words, both of these show low path length and high clustering. Nevertheless, in terms of their Laplacian spectrum, they differ very widely, and this means that in terms of the dynamical processes going on them, they would actually behave extremely differently. So if you look at how the timescale difference diverges with R, you can actually plot this particular spectral gap, the gap between the eigenvalue corresponding to, let's say, m, if m is the number of modules you have in the network, and the m plus 1th eigenvalue, and you can look at the difference of the reciprocal of these eigenvalues, which tells you by how much the timescales are different. And if you look at it as a function of r, you see that the smaller r is, the bigger is the difference. In other words, the sharper the difference in the timescales of the intermodular and intramodular processes. So you can now carry it over to the particular example we were looking at. So you can relate the timescale for the global diffusion, in how long it takes for the epidemic to spread through the entire network, as being related to the second eigenvalue. And the reciprocal of this second eigenvalue is essentially the timescale. And what you find is that this timescale comes down with R, which is what you expected, right? The more homogeneous the network is, the faster the epidemic spreads, so this is not surprising. But what you find is that the difference in the time scale, that also shows a very similar behavior. In other words, it also comes down with R. The better way to think of this is that as you decrease R, the difference in the time scales between the intermodular and intermodal processes also increase. Now, what is relevant for us is, of course, the ratio of these two time scales, because not only does the epidemic have to slow down enough in order to jump from one module to another, or in order to have enough susceptibles left by the time they come back, it also has to propagate fast enough through the entire network such that it does not die out while waiting to jump from one module to another. So there's a very tightrope walk to be done by the pathogen here. A, it has to jump quickly enough from one module to another, because if it waits in one module for long enough, it just dies out because it doesn't have enough, no susceptibles in that pool, right? On the other hand, if it jumps too quickly, then it spreads very fast to the entire system. So by the time it makes a complete production, nothing's left. I mean, everybody's either in the infected or the recovery mode. Okay, so it dies out. So if it can do this dance exactly, according to this optimal routine, such that it's just waiting long enough for it to jump from one module to another, so that it does not die out in the module it is currently in, and yet slow enough such that it comes back after enough time so that the original part in which it had an outbreak has become susceptible, then it can actually persist for eternity in the system, and that's actually given by the ratio of this two time scales. So if you look at the ratio of this time scale to the ratio of the global diffusion time scale, you find that the peak occurs precisely in that optimal range of R at which we saw the epidemic persistence probability to be peaking. So in other words, you can use an argument as simple as kind of a random walk or a diffusion process on a modular network and explain why epidemics would persist for extremely long times in modular networks. Essentially, the lesson is this, that contagion spreads slowly from module to module, allowing parts of the network to return before infection. All right, so what's the implication of all this? Well, one is that the way you combat a disease depends crucially on its basic reproduction number. You cannot have one-size-fits-all kind of public health policies for all kinds of diseases. So diseases which have low basic production number can be terminated with effective quarantining procedure, where what you're doing is you are just reducing R, small r, okay? So you are increasing the modularity of the social network. So effectively, you are decreasing the persistence probability of the disease simply by making sure that the disease cannot jump from one module to another, okay? On the other hand, if you have highly contagious diseases, so diseases with high basic production number, then isolating the communities may have the complete counterproductive implication of making the disease extremely long-lived. Okay? So you think that you have managed to isolate the disease to a particular module, but essentially what all you have done is you got to slow down the disease such that now it's going to, when it kind of does the whole circulation of the network, when it comes back, essentially it finds fresh meat. So the policies for highly contagious diseases, containing highly contagious diseases, has to be necessarily different from containing diseases with low values of basic production number. And it, of course, also tells you that in these two cases, you could have very different strategies. So here, for example, you could target specific groups which are categorized as high risk of infection depending on their role in connecting the different modules. Whereas in this case, you would essentially target individuals who connect otherwise isolated communities. Okay? All right. So, so that's the biological contagion part of the talk. And what I'll do is I'll just quickly change over to kind of a related but slightly different example where we look at social contagion and see now in this particular case, what role does modular organization play? So again, this is work done in collaboration with Chandrasekhar, and if you have questions, you could ask him afterwards. So while we were in the case of biological contagion, of course, the aim was just making sure that you don't have highly infectious diseases with high disease burden spreading through the community and becoming sustained. Here, the question is slightly different. So what we are asking is that, suppose you want to change public perception on something, let's say global warming, using an example which has already been quoted before. So how do you ensure success of these attempts? Okay. So of course you know that, individuals' opinions are not formed in vacuo. They are influenced by their peers. And so, one way of ensuring that you are successful in, getting your message across is to see that, the change in attitude which you want to see realized in the population has spread through a major part of the network which connects the entire population. Now, usually one way to ensure that people switch to your way of thinking is to make sure that mass media is covering, this fairly often and so on. But by itself, mass media may not be enough to tip individuals to change their habits, because typically, each of us are kind of resistant to change. There are various costs. Sometimes these costs are, overt. Sometimes these costs are much more, hidden. Like, for example, we just have to go against our ingrained habit of doing something, the same way. So we have to change our habits, and that involves some cost to us. So typically what happens is that if you belong to a group which is highly resistant to change, even though individually you might want to tip over, your group as a whole acts as a resistance to tipping over and adapting that other behavior. So here, again, we can ask, what is the role of communities or modules to which individuals belong in ensuring, let's say, the success or failure of some message or some kind of innovation to be adapted? And therefore, what we are looking at is how the existence of communities or modules affect the diffusion of innovation. So again, the starting point is the fact that social networks are modular, which we have already covered before. So just to jump ahead, so when you're studying diffusion of innovation, usually the starting point for many studies is a very well-known Bass model, which was proposed by Frank Bass back in 1969, which is like a meaningful description of how innovation spreads in a population. Okay? Now, the main point to note here is that this is essentially not very different from what I was talking so far. The Bass model is actually identical, mathematically speaking, to the susceptible infected compartmental model of epidemic spreading. So what you have is essentially you have people separated into two compartments. You have susceptibles and you have infecteds. And with some probability, the infecteds pass on their infection to the susceptibles. And there is also some intrinsic probability that someone who is not in contact with any infected would nevertheless get the infection. So this is termed as the coefficient of innovation. And the coefficient of imitation tells you what's the probability or what's the rate with which someone who has not yet caught the bug will catch the bug. So you can write down an effective equation where F is the fraction of population that has adopted that particular innovation. And therefore, 1 minus f is the fraction of population which has not yet adapted that particular innovation. And you want to ask what fraction of this susceptible population will catch the infection in the next step. So not surprisingly, this would be related to f, the number of people who has actually caught the bug at the moment. And the constant proportionality would be this coefficient of mutation. And then if you ignore this for the moment, so suppose f is 0 initially, the question is, would you have the infection spread at all? Now in biological contagion, you could say that even if the number of susceptible individuals is 0, the infection can still arrive from somewhere outside the population that you're interested in. So for example, in the case of India and H1N1, I said that if you just focus on the Indian population, then how did the initial infection start? It happens because some person flies in from somewhere else, lands at some international airport, and that's how the infection breaks out, right? So in this particular case, you can think of it like there would be a few individuals who are much more likely to adopt innovation, even though no one else around them has adopted it. So this would be essentially given by this coefficient of innovation, that they decide to adopt this even though no one else has adopted it yet. So now for different values of P and Q, we can see how F changes over time. So for example, if you look at the evolution of the fraction of population which has adopted that particular innovation, you find that with time there's a sigmoidal curve which describes how the population fraction who has adopted the innovation changes over time. So if you look at the likelihood that a person has adopted that innovation, you find that essentially for people who are adopting it simply because they have some intrinsic ability to adopt it, so basically they're not influenced by the people around them. So this particular goes down almost monotonically with time, whereas people who kind of adapt because of the social contagion, because of the fact that you have this Q, coefficient of imitation, which causes people to imitate others, so that would have a peak, precisely like in the case of the SI models of infection spreading, and then eventually it kind of goes down as you run out of people who have not yet adapted the disease. So again, you can think of it as susceptibles gradually running out, and so therefore, gradually it will go down to 0 as everyone essentially adapts. So you can put this mean field model on a network. So many people have studied this using some kind of a distributed context. So some people have studied it on spatial lattices, and others have studied it on networks. So one way of looking at it in a network context is to imagine that now you have a population of n agents, and each of them are represented by nodes of a network. And the nodes could be in one of two possible states, S or I. So you are interested to know at each time step what is the number of susceptibles at time t, and the complement of that would give you the number of infected individuals at time t. And now each link between a pair of nodes is the contact along which infection propagates, which in this particular case means that whether when you have adopted the innovation, you are likely to make your neighbor adopt that innovation. So now if you say that, let's say Q is the probability with which a person who has already adopted the innovation causes one of her neighbors to adopt the innovation, then you can write down the probability with which a susceptible node which has k-inf infected neighbors adopt that innovation is easy to write down in this form. So essentially 1 minus Q, so Q is, if you would like to see where this comes from, just think of it like this. So Q is this coefficient of imitation, or the probability with which if I am in contact with a person who has adopted the innovation, what's the likelihood that I will adopt that innovation? So the probability that I'll adopt the innovation because one of my neighbors has adopted it is Q. So the probability that I will not adopt is 1 minus Q. And the probability that I will not adopt it, given that all of this k-infected neighbors has adopted is this. So the probability that I will adopt it because of this is 1 minus this. And in addition, you also have this intrinsic probability, so that gives you this additional 1 minus p factor. So this, in the end, gives you this probability. So you use this probability to evaluate how the probability of innovation adoption will spread through the system, and you can study how the convergence time, or the time required for 98% of the population, say, to adopt this innovation, changes as a function of different rates of probability of adapting this innovation. So what we have done is that we have used a social network. So this is a kind of different social network from the one that I showed for the epidemic case, but again from the same set of 75 real social networks from Karnataka villages, which I mentioned. So here I'm looking at a group of almost 1,500 individuals, and I'm asking the question, what is the average time required for 98% of that population to adopt the innovation? And as you can see that this time required for 98% of the population to adapt the innovation, of course, decreases sharply with Q, the probability of, or the coefficient of imitation. But if you look at the corresponding randomized network, it's even faster. So that tells you that if you randomize the network, in the homogeneous network, the diffusion is occurring at an even faster rate. Of course, this difference becomes smaller and smaller as you also put in other things, like, for example, if you say that not only does innovation spread only through imitation, it can also spread through innovation, then essentially the difference of the random and the empirical networks almost disappear. So you can say that here the role of modularity or the role of community organization is almost absent. This is just a fraction of people who have adapted the innovation with time, and again you can see that the difference between the random and the empirical networks is quite close. Sorry, it's almost negligible. Now the problem with BAS model is that because it's an SI model, any innovation which enters into the system, it's almost destined to spread through the system. Okay, it's like an SI model. I mean, you start an infection and it will spread through the system, eventually getting everyone. So it cannot explain things like, for example, why is it that certain innovations get adapted very rapidly, but others of almost similar caliber don't get adapted at all. Okay. Nor can it explain why is it that fairly similar innovations spread at very different rates through the system. And finally, it does not capture the cooperative nature of interactions within social groups, where you're much more likely to catch the bug if you know that 3 of your neighbors have already adopted it than if only one has. Okay? So this positive reinforcement between your neighbors, saying that, oh, you know what, I've bought this new fridge and it's excellent, and your friend says, oh yeah, I have also bought that fridge, and and then another friend hearing this said, yeah, I heard the 2 of them, so I bought this fridge and it's excellent. So you're much more likely to adopt that. Okay? So there's some kind of a nonlinear interaction over here, which is not quite captured by the BAS model. So one way to introduce these kinds of effects is to look at a slightly different approach to studying diffusion of innovation, where you use what physicists would call a spin-like model of innovation adoption. So in such spin models, essentially you say that each node can again be in 2 possible states, with, just for fun, let's say we call it +1 and -1. So essentially this allows us to indulge in physicists' fantasies of imagining that people exist in 2 varieties, up arrow and down arrow, or up spin and down spin. And that quickly helps us to write down it in terms of an energy minimization paradigm. Okay? So what we say is that, suppose you have in the network all these different individuals whose, whether they have adapted or not adapted can be represented by, this +1 or -1. So adaption means +1 and non-adaption means -1. So the behavior of the entire network I can write down in terms of an energy function, where the different terms present, first of all, this social contagion effect, where you say that, because of what my neighbor does, I am more or less likely to do something, where Gij essentially is giving me the interaction strength. So if J is equal to 0, frankly, I cannot care less what J thinks about a particular innovation. But if J is high, then obviously J's decision to adapt or not adapt has a very big role to play in whether I is going to adapt or not. So think of it like this. Essentially, this term is telling the individuals to follow what the neighbor does. So you would like to do what your neighbor does. Okay? In other words, you would like your state to align with that of your neighbor if J is a large positive quantity. Okay? Because that essentially results in bringing down the energy, and essentially this whole paradigm is about energy minimization. What about this term? So this term is essentially like a threshold. So this tells you that, if different individuals may differ in terms of their intrinsic threshold, so some people may be more resistant to change, some people may be less resistant to change. So this intrinsic differences is being captured by the distribution of these thetas. And finally, you have the role of mass media captured by this term, where H is something like, the perceived advantage of an innovation, which is common to everyone. Okay, so it's like, you go into the, television and sing the praises of the latest invention of a particular company, and you hope to God that people will listen to you. But of course, this is only just one of the various influences which play a role in deciding whether I is going to adapt the innovation or not. Okay? So I have essentially interaction between individuals, which is like describing how the social contagion process results in a particular individual switching to the innovation or not. You have local thresholds of the agents which decide whether they are susceptible to a particular media campaign or not, to the pressure of the social peers. And finally, you have the perceived advantage of the innovation being adapted. So the bigger H is, presumably the more successful your mass media campaign, or so on. Of course, the product may be so good that you don't even need a mass media campaign. So nevertheless, its H will still be high because everybody perceives it as wonderful. So, like, let's say it's not a product, it's let's say some moral, percept, do not steal or do not kill, okay? So H is high, even though you don't require mass media campaigns to promote it, right? So, so these are the three different, terms. Now, if you didn't have these fields, okay, so I call this a local field because you can see that it has a formal similarity with the way that this term is treated, except that instead of a global parameter, this is like a local parameter. So that's why I call it a local field and this one a global field. So if you didn't have these fields, if you just had this, and you studied how a modular network is going to actually play out this coordination process, even that is actually fairly interesting. So if you have a modular network on which you have these spins aligned in certain ways, and you ask what kinds of eventual ordering would be shown by such a system, you actually can show that there are two possibilities. You can either have a modular order in which within each module you have complete alignment. People agree with each other within their modules, but you have complete disagreement between modules. So for example, everyone over here has decided to be -1, everyone over here has decided to be +1, and while there is complete local agreement, there is global disagreement. Okay? Whereas over here, there is complete local order as well as global order. Everyone has agreed to be +1, not only within their own modules, but also across all the modules. Okay? Now, it's possible to go through the entire maths, but I will just skip through it because it may not interest everyone. Suffice it to say that you can work out the free energy calculations, you can minimize the free energy with respect to the state of individual modules, and at the end, you would be able to derive, in some sense, critical temperatures at which you would have a switch in the system from no order to local order, and then local order to global order. So what do I mean by temperature? So temperature over here is like a noise, which essentially says that, if you look at just the different influences coming to you, you might have switched, but because you're not confident that the information that you're getting is correct, or because you're just ornery, you just want to be contrary to what others do, you decide to do something else. Okay? So the more different you are, different your action is compared to what you'd expect from these different influences, the higher the temperature. Okay? It's a measure of this environmental noise, which in some sense randomizes your actions. So at the limit of extremely high temperature, essentially you are just switching to +1 or -1 with equal probability. Okay, the influences don't matter at all. Whereas in the other limit, temperature going to 0, it means you do precisely what your inputs are telling you. You just evaluate, how many of your neighbors have switched to the other decision. If more have switched to the other decision, you decide to go along with them. So it's like a majority rule. Remember, there are no fields here. All right, so just like we saw in the epidemic case, here we have the axis along which we vary the ratio of the intermodular connection density to intramodular connection density. In other words, in this limit, we have homogeneous random network, and somewhere in this limit, extremity of this, you will have completely isolated modules. And along this axis, we have increasing noise. The temperature essentially increases. So as I was mentioning, if you have extremely high noise, so that everybody is like flipping back and forth, +1 and -1 with equal probability, there's no order, right? At any given point of time, you can come and look at your system, and you'll find roughly half of them +1, half of them -1, so that the global order parameter as well as the local order parameter is 0. Okay? And so that's what this colored region indicates. What happens when you have temperatures lower than this? So let's first look at this region, the green region. So over here, you have local order as well as global order. In other words, not only have all your modules aligned, so everybody within a particular module has agreed with everyone else in that particular module, but you also have all the modules aligned along the same direction. So essentially, you have complete unanimity in society. Contrast that with this particular region, where you have no global order, but local order. So essentially, what you have here is each module, individuals agree with everyone else in their module, but two different modules would have complete different agreements. So, one module decides +1, the other module decides -1. So the surprising behavior essentially is this, that here, every interaction essentially is a positive interaction. In other words, whenever you have a social contact with another individual, the social contact is always trying to make the two of you align your opinions. Okay? In other words, these are agreement-inducing contacts. You would like to agree with everyone else, right? And that's pretty much what happens in this limit when you have a homogeneous contact network. Everybody decides to agree with everyone else so that everyone switches to +1 or everyone switches to -1. But if you have a highly modular network, for an optimal range of noise, what you find is that even though everyone wants to agree with everyone else, you end up in a situation where you have clusters of people who strongly disagree with everyone in the other community. Okay? So people have no desire to be antagonistic. The social structure somehow causes complete opposition emerging out of the dynamics. Okay? It's essentially the community organization which is causing this occurrence of strongly opposite opinions being held by different communities. Individually, each of them would, of course, like to agree with everyone else. So coexistence of contrary opinions in that sense is essentially a network emergent property. So now suppose you switch on the fields, you bring in both this local threshold, local fields which essentially model the thresholds of individuals for adapting a particular innovation. Yeah. No, when you say friends, what do you mean? So, one of the examples I used to give in some other talks was precisely that if you have two modules, then in this setting, where, take the case of this. So you have just two communities, okay? And you have a few links which connect them. So all of these links are positive links, or in other words, alignment-inducing links. Nevertheless, you would end up in a situation where all of these are up and all of these are down. Okay? So the few individuals who kind of span across the, So these individuals are friends with these individuals, okay? So the reason why, despite having links between these modules, you cannot have broad agreement across the population is because how would you even start this process? So let's say in order to ensure that this community aligns with this, you first have to start small, right? So you have to first make sure that the individuals who are directly connected over here flip their orientation, and then it can start spreading. But the moment these guys flip their orientation, their peers in the community they belong to bring them down, right? So essentially there is this contest between. Okay, so here there is no dynamics of the network. So there is only dynamics on the network.
From your result, what can I derive that? Dynamically those connections.
See, if you want to bring in reconfiguration of links, or if you want to bring in a weight dynamics, that actually brings in a further complexity. And yes, we have looked at that and tried to see, for example, how starting from a homogeneous network, you can actually spontaneously, get this kind of a network. So actually there, both kinds of things can happen. You can either have a merger in which, initially separate clusters eventually merge, or you could have further fragmentation where, you can have one large giant cluster to begin with, and then it spontaneously segregates into two separate clusters. So bringing in this reconfiguration of links can actually, go both ways. Depends critically on the, system parameters and so on. Right. So I don't quite understand this stable opinion business, but so one way to think about would be, for example, suppose you have some opinion -1, and you have friends in the other camp who have opinion +1. What is the probability that you would change your opinion? Okay. Now the problem is, of course, if there is sufficient amount of modular organization. Now, if you just have too many links connecting these two modules, of course, eventually you will switch. You would become part of the other module. Okay? But if you have too few links connecting them, even though you might have friends in the other camp, that's not enough to, let's say, counter the effect of your social peers in your own module. Okay? So, yeah, we can talk about that later. Yeah. So now introducing these fields in order to study in particular how innovation spreads in the model network, you can ask, okay, suppose now I have this H parameter, which essentially measures the perceived advantage of innovation. So the bigger H is, the more likely I am to adapt it, which is pretty much what is seen, right? So if you have a homogeneous network, essentially you have at some critical value of H, suddenly a very sharp rise in the number of people who have adapted that innovation. So essentially it goes from 0 to 1 at a critical value of H. And on the other hand, in the case where it's extremely modular, this critical fraction actually goes to a much higher value of H. Not only that, the transition also becomes much more gradual, right? So that's one way to look at this. Another way to look at this is now to study this dynamics on these real social networks that I've already introduced in the context of biological epidemics. So you can look at each of these villages and you ask that, okay, suppose you had the innovation started at some point, how does that spread through the rest of the population? So it turns out that it depends very crucially not on just the model organization, but also on how the individual who starts this innovation is connected, or what its role is vis-a-vis the modules to which it belongs. So, you can measure the nodes or the importance of the nodes in terms of what role they play in the modular organization of their network. So this could be, for example, characterized by two parameters. One is the intramodular connectivity, which is defined in terms of the within module degree statistical significance. and the other is the extramodular connectivity, which is defined in terms of participation coefficient. So I'd like to use an analogy here. So suppose, so what is the analogs of these things? So suppose you, come to ICTS and you want to find out who are the, social movers and shakers of ICTS. So one way is to just hang around in the canteen and see who is it, or who are the people with whom most people talk to. Okay, so that's like the extramodular connectivity, because these people could be talking to people not necessarily in their departments, right? They could be talking to people all across. So by looking at how many contacts do you have across your community to other communities, you get a sense of the participation coefficient of the particular node. What role or how important role does it play in connecting the different modules? On the other hand, you might be just interested to see that within a particular department, how important a person is. Okay, so you just go to the departmental seminars and so on, and after the talk is over, you see who is it that people are mostly talking to. I mean, apart from the speaker. Okay, so that's one way of figuring out that within a particular department, who is it that students most talk to, and so on. And so that gives you an impression of the within module degree or within module importance. So how is it that a node is placed with vis-a-vis its own module? Is it playing a very important role in its own module? So these two measures can give complementary information, because you could have nodes which are very important in terms of their own module, but has very little connection outside its module. On the other hand, you could have nodes which is like unimportant in respect of its own module. It doesn't have too many contacts with its own module, but it plays a very important role in actually making sure that the module is connected to many other modules. We all know friends, right? I mean, who has, friends all over. And, typically it's this person through which we get information which we otherwise would not have got, okay? So by categorizing nodes in terms of the intramodular connectivity and extramodular connectivity, we get an additional dimension, some additional information, apart from just the modular structure of the network. So, you can characterize nodes in terms of their participation coefficient and within module degree Z-score by, categorizing them as non-hub nodes and hub nodes, and then within hub nodes, you could call them connector hubs and provincial hubs and so on. So all of this is like detailed by Gomera and Amaral in this very nice paper. Okay. So now that we have these kinds of parameters to characterize nodes, and also we know what modules each of these nodes have, let's look at a couple of simulations. The first one is where we have successful adaptation of an innovation. So by the way, both the simulations that I will show you uses exactly the same value of h. So in other words, the perceived advantage of the innovation is same in both cases. But in one case, we will see that it's successfully spreading throughout the network. In the other case, it will fail. So in this case, you start out with, let's say, the innovators being here and here. And then as time progresses, you find that it spreads through the entire system. So by about 130 Monte Carlo steps, essentially it has covered almost the entire system. By contrast, if the innovation started somewhere here, so one thing I forgot to tell you is that the size of these nodes are actually, in some sense, representing their role in terms of this, whether they are have a high intramodular connectivity and intermodular connectivity, or they have low intramodular connectivity and low intermodular connectivity. So the bigger the node, so the bigger the node, that means, so the biggest nodes, for example, have high intermodular connectivity as well as intramodular connectivity. The intermediate sized nodes have high intermodular connectivity, but not necessarily high intramodular connectivity. And finally, the smallest nodes have low numbers for both. Okay, so in this particular case, we start out the innovation with an individual who's not a very important player either in its own module or across modules. So what you find is that it does not actually spread at all. It remains confined to just this particular section. So here, not only is the modular organization playing a very important role, which node starts out this innovation is also playing an important role. In particular, if we can figure out what is its role vis-a-vis its modular organization, that is whether it has high within module degree or high participation coefficient, that can give you a very good idea of the future success or failure of this innovation. Yeah. It might, yes. So this is, we are just talking in terms of probabilities. Okay. So if you start the innovation with someone who doesn't have high within module degree Z score or high participation coefficient, it's that much more less likely that eventually it's going to break out into the system. So you can actually now target. So if you are, trying to ensure that it's going to spread out, you can target individuals based upon their within module degree Z score and participation coefficient. Yeah. Okay, so that is a difficult question. So because these are real social networks in which we cannot control all of these variables, it's very hard because we just have 75 different examples. So we just have 75 different ways in which you can vary this. But it looks like that intermodular connectivity actually plays a slightly more important role than intramodular connectivity. Yeah. Not necessarily, not necessarily. Yeah, so but you can identify individuals who actually satisfy this criterion. So these are the so-called kinless hubs, okay, which have high intermodular connectivity, but quite low intramodular connectivity. So, as I said in response to his query, I mean, we have only 75 different examples, so we can't actually do a systematic study and try to see that if you increase the number of kinless hubs, whether you increase the success of innovation adoption. But it looks like kinless hubs have a slightly better chance than, let's say, non-hubs, which just happen to have sufficiently large number of connections within their modules. Okay, so this is this is still something that we have not been able to do a control study of. This is just some result which suggests that this role that they play in terms of the model organization has a very big, important bearing on deciding the future success of the innovation. So, this is how the convergence time of the, adoption of innovation fares as a result of these different parameters. So, let me just, focus on this particular slide because I'm run out of time. So, essentially, what you have here is, okay, let's just focus on first this two red curves, ON empirical and ON rand. So here what I'm comparing is the original empirical social network with its corresponding degree preserved randomized surrogate. Okay. Now, notice anything surprising? Based on what I've already mentioned. Okay, I guess it's slightly hard because there are four other curves. There are two other curves here. Let me tell you the surprising part. The surprising part is that innovation actually spreads faster in the empirical network than in the corresponding randomized network, which runs completely counter to everything I've said so far. Okay. So initially when we saw this, we were like really surprised that how come this general truth which we thought to be, universal, that whenever you have a structured network, typically diffusion occurs much more slowly than the corresponding empirical network. How come this was completely flipped? How come the real network actually causes diffusion to spread faster? Okay, so what we did was we then went to the network and started taking out several of these intermodular links, and then we saw that if we take out enough intermodular links, actually the story that we know to be true is again established. So, for example, if you reduce the empirical network by reducing a large fraction of its intermodular connections, and then you compare it with this random degree preserved network, you find that here, as before, as in the other studies, diffusion occurs much faster in the random network compared to the empirical network. So then the question was, what is different about this empirical social network? So what is different is, of course, the occurrence of these connector hubs. Okay. So when you take out this large fraction of the intermodular connections, what you're doing is you're reducing the role of the connector hubs. You are just making them very similar to the other, kinless hubs in the system. Not really, right? So if you see, for example, in this network, there's a very tight clustering. You really don't have stars where you have a single individual which has lots and lots of connections. Okay. So I don't think that it's that simple an explanation, but you are right that it has something to do with the occurrence of connector hubs in the system. So it's this connector hubs or the network formed by this connector hub which actually causes innovation to spread extremely fast through the system, much faster than would have happened had you just had a corresponding randomized network. All right, so let me end by just reiterating what I've already mentioned before, that essentially the surprise part here is that apart from the usual things that we usually associate with random modular network, that random modular network slows down spreading process and so on, the surprising part was somehow the functional role of nodes in terms of their position in the modular organization plays a very important role. In particular, in the empirical social networks that we are studying, spreading or innovation adaptation occurs much faster than in the corresponding random homogeneous network. Okay, so let me stop at this point, and I'd be happy to ask questions. I'm sorry I never had an opportunity to go to the other theme which I wanted to explore, which is games, but Shakti would be there to talk more about it.
Questions? Chris?
Yeah, that's a great idea. I believe it should. Yeah, so as I said, our limitation was we were just focusing on the social network. So we should maybe look at models where we can tune this degree correlation and study this adaptation process. That's a great idea. Thanks. Right, it's assortative. Yes, degree assortative. That's true. Yeah.
Other questions? No, so I don't quite agree on that, because so what we did was we proved that there exist phases, or there exist a combination of R and T, where actually no matter how long you wait, they will never agree. So that was the what I was trying to show using this. Yeah. Right. Yeah. So these are all results for infinite systems. That's true. So the energy function, the Hamiltonian argument that I was giving is holding strictly true only for infinite system. That's true. But we did simulations with extremely large networks, where we carried out the simulations for extremely long times and didn't see convergence, which leads us to believe that maybe we see this thermodynamic limit behavior even at moderately sized networks. In fact, there turned out to be an interesting point associated with this. So you remember that I said that the phase diagram looks a bit like this. So if you vary R and if you vary T, or rather something related to T, it was roughly something like this. So here you have local order. So here I agree to disagree. Here you have global order. I agree to agree. And here you have disorder. Okay, so now when we try to do numerics on this, and we initially first tried straightforward Monte Carlo, the numerically obtained phase diagram, in fact, looked something like this. Okay, and we were initially very puzzled. Why is it that the phase diagram looks like this? In fact, originally the student who was working on this had just done numerics, and based on numerics had come up with a phase diagram which looked something like this. So global order, local order, and disorder. So then when we had the actual analytical argument, we went back to this and wanted to see why was the numerics disagreeing. And we realized that what's happening here is that there is extreme slowing down of the dynamics because of the extreme low temperatures that we're talking about. And so, eventually, in this range, you would have flipping. You would have, systems going to global order. So, you started with a system which is like, aligned in opposite directions, but if you wait long enough, they would go to the same order. It's just that it's taking extremely long times. So then we had to, use other variants of Monte Carlo mechanism, which takes care of this slowing down in order to, and then, sure enough, we saw that it's this phase diagram which emerged. But I, completely agree with your point that you could have actually slowing down behavior, which would make you seem as if this belongs to local order, when in reality it is not. If you wait long enough, it will actually flip. And so we have actually now characterized even this slowing down processes. So in fact, we know how exactly the dynamical timescales slow down in this range and how it's related to R, for example.